We will start our discussion of sequential circuit timing by discussing some flip-flop timing parameters. So timing parameters applies to a single flip-flop or a bunch of flip-flop. What I'm saying is timing parameter also applies to registers. But for simplicity and for our discussion, I'll only focus on a single D flip-flop. It can be either JK or T flip-flop, but for simplicity, we're just going to focus on D flip-flop. And we're going to focus on a D flip-flop that samples D at the positive edge of the clock in here. So the active edge is the one that goes from 0 to 1. And in here, I'm showing you some timing diagram, and these timing diagram also show the timing parameters. So let's discuss them. I might have mentioned before that the input to a flip-flop, no matter what it is, no matter what type it is, has to be stable for a certain period of time around the active edge of the clock. Specifically, what I meant by that is the following. That if you have an input or inputs, if we're talking about registers, that input around an active edge of the clock, so this is the active edge of the clock, this is when it goes from 0 to 1. So let's say that this is the active edge of the clock exactly. What I need for this input to be stable around that active edge of the clock. And more specifically, I want it to be stable for setup time. This is what we call it, right before the active edge of the clock. So from here to here, this is actually what we call the setup time in here. And I also need it to be stable after the active edge of the clock for what we call the hold time. So these are T setup and T hold. All right, so stable meaning that it's either at 1 and it stays at 1, or it was at 0 and it stays at 0 right after the edge of the clock. After these times, it is fine for the input or inputs to change. Okay, so this is what we call setup time and a hold time. And more interestingly, as it turns out, that these here, the time from here to here, basically the combination of T setup and T hold is what we sometimes call the aperture time. Okay, so the aperture time or the aperture window, sometimes I refer to it. And it's coming from a camera perspective. And we'll talk about why we call it that way when we talk about metastability. But for now, all you need to know is an active edge of the clock comes in. You need to stabilize the signal before it and after it for a very specific period of time. And if you have done this, that means you did not violate any of the timing constraints, any of the hold time or the setup time was not violated. So you didn't go from 1 to 0 within that, or you didn't go from 0 to 1 within that aperture window. The output Q here would reflect whatever you put in the input. However, the time it takes from the active edge of the clock till the input, or from an active edge, which is a positive edge in here, till the output here actually gets changed, is what we call a clock to Q, okay, or what we call a clock to Q, okay, CQ. And as it turns out, this diagram is showing me a couple of things. It's showing me a couple of clock to Q times, and one is the short version. Basically, I have a certain range. It's a short version, okay, and the short version here is what we call the contamination, all right, and or what we call sometimes the propagation delay. All right, so what's the difference between contamination delay and propagation delay? Well, depending on how we construct that flip-flops and the type of transistors that we use in them and the different capacitors and the tolerances and the manufacturing. So we usually get some sort of a range that tells me an active edge of the clock comes in. It will take between this number and this number for the clock to appear. So contamination is actually the shortest number. So what we see in here is actually the outputs. So what we have this is the active edge of the clock. We stabilize the input regardless of what we stabilize them at, 1 or 0. After the active edge of the clock, the earliest it appears is actually what we call the contamination clock to Q, and the maximum delay that we have to wait for the output to actually be stabilized or to actually be done, or it appears at Q, it's actually what we call a propagation clock to Q. You might not see contamination or propagation. You have to think about them as minimum and maximum. Some data sheets actually refer to them as contamination and propagation. That's why I'm using them. All right, so where do we get these numbers from? Well, usually you refer to the data sheet. So in here, I'm showing you the data sheet for the 7474, which is a dual or 2D flip-flop, and both of them will be active on the positive edge of the clock, and both of them will have a preset and clear. Basically, you can set and they're asynchronous preset and clear. But anyway, so what I did is I selected certain tables that are actually referred to timing, and I'm just going to highlight them in here. So this one here is what is called the setup time. Okay, so of course we have a couple of them like 5474 and 7474. There's like slight differences. Both of them will have D flip-flop. But anyway, we're just going to focus on the 7474 here. So what this tells me is the setup time is 20 nanoseconds. So this means that I have like this time in here, the setup time in here, I have to stabilize that signal for at least 20 nanoseconds before the active edge of the clock. And the line right after it tells me the hold time is actually 5 nanosecond, which means that this signal in here has to be stable for 5 nanosecond after it. So in total, the aperture, if you think about it, it's 20 plus 5, it's 25 nanosecond. It has to be stabilized for 25 nanoseconds total. Of course, this will change depending on the temperature and whatnot, but in general, these are the numbers we use in our normal operation. These tells me that this is the normal operation. And the contamination to clock, or the contamination of the propagation, or specifically the clock to Q, depending on the data sheet and the manufacturer, you're going to see them differently. But they usually stem from the fact that you might be going from like the output, this one here, this output 0 might be either going from 0 to 1 or 1 to 0. Okay, so it's either it was 0, then it goes to 1, or 1 goes to 0. And it's, as it turns out, the time it needs to go from 0 to 1 or 1 to 0 are different, and that's why we have these ranges. So the second table in here shows me the following. It shows me actually a few of them. It shows me P, L to H, or low to high, and then this is high to low. Okay, regardless of the meaning of it, and I see a bunch of numbers, 4 of them, and the reason why is because it's giving me that clock to Q. They're not all clock to Q. For example, this is not from the clock. This tells me that it will be as a result of hitting the preset or the clear. These are the asynchronous one. If we care only about the clock to Q, we need something from clock, and it tells me that the output it's either Q or Q prime will be set. So these are the actual clock to Q in here, the last 2 numbers in here. And what I care about is this number in here and this number in here. So obviously this is the minimum number, which I would refer to as the contamination, which is 25 nanoseconds, and this one here is 40 nanosecond, which is the propagation delay. So if I go in here and I just want to, I'm gonna clear a little bit here. I'm gonna clear this figure a little bit, and let's write these numbers in there. So these numbers tells me the following. It tells me that the setup time is 20 nanosecond, and the hold time is 5 nanosecond, and it tells me, I believe it takes 25 and 40. So this one here is 25 nanosecond, and this one here is 40 nanosecond, and this is what we get out of the data sheet.